Welcome to Data Science with EJD. In this video, we will talk about practical tips and engineering for reinforcement learning. So I mean, just like I've done for every video, I've been putting together so many ideas that probably maybe one of each section should actually make for a separate video. But I just think at this point I'm just introducing the whole idea so that if you are really interested in these things, you can then deepen your knowledge in them. You can take these things further. So let's go ahead, talk about practical tips and engineering for reinforcement learning. The first part will be looking at debugging reinforcement learning agents systematically. And the objectives of that will be to identify and resolve bugs in reinforcement learning pipelines and to develop strategies to monitor and inspect agent behavior. Don't forget, reinforcement learning is that branch of machine learning where there's an agent in an environment taking certain actions based on whatever current state they find themselves, and any action they take changes their state, either for good or bad, because a reward is attached to every action taken, and every agent. And where machine learning comes into that is that the agent learns the behavior that gives the best rewards and sticks to that more often than not. Okay, so the breakdown of that will be to start working with a working baseline, like use well-tested implementations like stable baseline 3, which we've been using for some videos now, and then clean reinforcement learning or spinning up. Then the component-wise debugging would involve environment where you check observation, reward, and action validity and ensure determinism if required. Then you talk about the policy network where you confirm correct output shape, check for not available data and validate action range. You can also replay buffer and where you inspect sampling logic and correctness of stored observations. And then we can talk about loss functions where you monitor gradient flow, magnitude, and numerical stability. So there can also be behavior inspection. Don't forget, we are talking about debugging reinforcement learning agents systematically. So there can be behavior inspection where we render environments using env.render or record episodes using monitor. Then you can log actions, Q values, and entropy over time for inspection. Then you can have unit tests for components. So you can have different tests like value function updates, replay buffer insertions, terminal state handling, and episode resets. Then there are common symptoms like flat reward curve. You have issue in reward function, loss computation, or sampling. Then not available numbers. So you have you have numerical instability, the large gradients, or log zero. Like when you divide by zero, or you take the log of zero, so you're going to get an undefined number. So that will lead to NANs. Then you have zero gradients, which leads to dead activations, e.g., you have RELU or poor weight initialization. And you have constant action like entropy collapse, poor exploration policy. Then the tools and techniques you would need for that would be PDB, PyTest, assert statements, visualization tools you would need would include Matplotlib and Gym.monitoring. Video logging, you need FFM, PAEG, and OpenCV. And for weight and gradient visualization, you need TensorBoard. In fact, in the next video, we'll be doing something like a capstone project that will involve the use of TensorBoard and Dash for making a dashboard. Second section, we talk about hyperparameter tuning. We're talking about practical tips for reinforcement learning and some engineering that may be necessary. So hyperparameter tuning in reinforcement learning. The objectives here will be to learn the impact of key hyperparameters, apply search algorithms to improve training efficiency. So some key parameters here will be the learning rate, gamma. Learning rate, that's one. And then you have gamma, which is the discount factor. We've talked about that a lot. And then the entropy coefficient. Then we'll have other parameters like batch size, buffer size, target update interval. And then there's PPO clip, epsilon, A2C, GAE, lambda. So the project in the next video is about PPO, that's primal policy optimization, I believe. So the systematic tuning process now, the first thing is to select target metric like cumulative reward of success rate, and two, you select search method like grid search for low dimensional tuning, random search for broader exploration, Bayesian optimization. You use tools like Optuner and ASHA/hyperband where you use early stopping of underperforming runs. Then you have automated tools like Optuner, Raytune, weights and biases, W&B sweeps, and then there's for visualization you have parallel coordinate plots, and then you have contour plots of reward versus parameters. So And best practices in this regard would include using consistent seeds for reproducibility. We've done this a lot since we started talking about machine learning. Then there's running of multiple trials per configuration to account for variance and then log everything. So hyperparameters, perform metrics, and run metadata. And then you apply domain knowledge to reduce and prioritize the search space. So you need to use the domain knowledge of whatever space you're working in so you can actually, make the best decisions that align with the field your data is from. Okay. You have reward shaping and engineering, and the learning objectives there will be to design reward functions aligned with task goals, mitigate undesired agent behaviors, and the concepts would include things like sparse versus dense rewards. Sparse is only a terminal state, while dense is step-by-step progress toward the goal. And then there's potential-based shaping, where you keep optimal policies invariant, and you have phi of S, which leads to shape reward, and that is you have R prime equals R plus gamma phi of S prime minus phi of S. That's potential based shaping. And then you can avoid reward hacking so you monitor for unintended behaviors, e.g., working in circles or add constraint via auxiliary rewards. And then you can have multi-objective reward design. So you have weighted sum of objectives where R is W1 times R1 plus W2 times R2 and so on and so forth. And then you can normalize or balance reward scales. And there's real world examples of this, like robotic reach task, where reward is equal to negative of the distance to goal plus negative of penalty for joint talk. Then you have toolkits in that regard involving gym.reward wrapper for custom reward logic, and then you have logging individual reward terms for analysis. So this is a combination of several things that work in reinforcement learning. So for 4, you have monitoring and visualizing with TensorBoard. The learning objectives there will be to track and debug model performance over time and understand the internal dynamics of the agent. And the setup is you use summary writer from touch.utils.tensorboard, and then you log the scalars like reward, loss, learning rate. Then you need histogram for weights and biases, and then you need images and videos for rendered episodes, and you need text for reward function, annotations, and config. Then tracking essentials, you need episode return like mean, maximum, and standard deviation. Then you need loss breakdown like policy, value, entropy. You need action entropy like exploration proxy. You need value estimates under or overestimation of whatever values you're talking about. Then learning rate schedules and gradient norms. Then there are advanced features like adding custom scalars, e.g., success rate, win percent, or use TensorBoard projector for embedding visualization. So in 5, you have to choose the right reinforcement learning algorithm. So the learning objectives here, you can choose appropriate algorithms based on task constraints and understand the trade-offs between value-based, policy-based, and model-based reinforcement learning, right? You remember value-based learning like QNet, deep Q networks and all and things like that. And then we talked about policy-based, or we talked about prediction-free and all of those things. So then you have, let's look at algorithm. Algorithm comparison table. So if you have the task type, preferred algorithm, and the notes. So you have discrete actions plus low dimension. So you use DQN or WDQN, and the notes include you have Atari-like tasks. Then for continuous control, you can use PPO, that's primal policy optimization, and SAC. So for things like robotics and Mojoko, then you have high sample cost. So you have model-based reinforcement learning like Dreamer and MBPO. It's for the efficiency is critical. Then partial observability. You have A3C plus RNN slash PPO plus LSTM. That should be long short TM. I've forgotten what TM is now. Long shorts. I think it's some algorithm for time series analysis, right? So, okay, long short-term memory. I remember now. So the notes memory needed. Then for offline, you have offline stroke batch reinforcement learning. You have things like BCQ, CQL, AWAC. No environment access in this case. So you have multi-agent reinforcement learning where you have algorithms like MADDPG, and QMix. The notes take note that this is competitive. Here you have competitive and cooperative tasks. So when you have multi-agent reinforcement learning, you have more than one agent interacting in an environment. So the decision framework now, you have the action space, which is discrete or continuous, environment, which can be discrete or continuous, like, right? Then you have environment cost, which is cheap or expensive to simulate. Policy stability, is it on policy or off policy, like we've seen before? Latency needs, is it real time or not? Okay. Of course, you remember that batch reinforcement learning is not real time. It uses available data to make decisions, right? So scaling experiments with vectorized environments. So the learning objectives in this case will be to accelerate training through parallelization and understand how to manage multiple environments. So the concept, so looking at the concept, why do we have to vectorize? Why vectorization? Because it reduces sample correlation, faster batch generation. It leads to faster batch generation, that is, and it stabilizes learning via average performance. Then we can have synchronous and asynchronous. For synchronous, it is deterministic and easier, and it can be debugged more easier debugging, that is. Then for asynchronous, it has higher throughput and harder to reproduce. Then implementation tools include things like gym.vector, subpro vector environment, dummy vector environment. Then you have stable dash baseline 3 integration. Then for batching now, you have forward pass on batch of states and backward pass on batch loss. The challenges include RAM and CPU constraints. That's random access memory, right? And central processing unit constraints. And then you have seed management and reproducibility. So exercises, you can train a PPO with 1, 4, 8, and 16 environments and compare speed up and convergence. Then you can use PSUTIL to monitor CPU usage. Then we have a seventh one, uh, which is building a custom training dashboard using either Streamlit or Dash. I think I've used Streamlit a couple of times, but I mean I prefer the results I get with Dash. So in the project we're going to do the capstone project in the next video, we are going to be using Dash instead of Streamlit. But I guess Streamlit has its own advantages somehow. But I mean, using this environment I have doesn't just work perfectly with that for now. I think I need some extra things like, using bash and all that, or using command directory or things like that. Using the command terminal, some also. So learning objectives, you can visualize training data in real time and create interactive widgets for monitoring and control. So components of the dashboard will include reward curves, smoothed and raw, action distributions for each time step or episode, policy loss or value loss trends, performance metrics like success rate collisions, task specific KPIs, environment snapshots, like video or image previews, hyperparameter viewer, what config led to best results. We want to see all of that. So at the back end, we can use CSV, JSON, or SQLite as log format, and we can update file every N episodes with new metrics. I think we are going to demonstrate that in the project too. Then for the front end, you have a Streamlit example. Because we don't have any log file right now, that's why I'm just keeping this raw because we don't actually have a CSV file that contains things like that. So that's what, but this is a typical way to use Streamlit for the front end. Then for optional features, you can add a restart or pause or resume button. You can compare runs using a drop-down menu, and you can display hyperparameter search history. You can integrate with weights and biases. That's W and B, or machine learning flow, ML flow, that is. So we have a suggested project, which is end-to-end reinforcement learning engineering. We're going to do this project in the next video. That'll be the capstone project for reinforcement learning. And I feel that for now, I'm going to with the next video, I'm going to move on to, by popular demand, Microsoft Excel. I've been trying to dodge that all this while, but now I think based on popular demand, I have to do a playlist on Microsoft Excel because I mean the whole data thing, of course, has to start with Microsoft Excel, then before you move to, say, SQL and then Python, for different aspects of the way to data science, right? So in the next video, we'll be doing a capstone project on training and monitoring a primal policy optimization agent on a custom maze using TensorBoard and Dash. And we're going to take the following steps. Once we implement environments in Gymnasium, that's an open AI thing for reinforcement learning. Then we design reward shaping strategy. Then we train with PPO using stable dash baseline 3, and we tune learning rate and entropy coefficient with Optuna. Then we log training data to TensorBoard, build a real-time dashboard with Dash. We can do this with Streamlit also. but I'm using Dash in that capstone project, and we evaluate agents and held out maze layouts. So watch out for this. That's what is coming in the next video. So with this, we come to the end of this particular video. Thank you so much for listening. Let me know how helpful this is for you. If there's something you'd like me to try out, feel free to let me know. And if you have subscribed already, thank you so much. If you have not subscribed, please go ahead and subscribe and hit the notification bell so you can always get alerted each time any video is released. You can become a member of the channel. Just click on join and you see different layers of membership and the perks attached to those. So one of it would be, things like having some videos exclusively made for members, so just look around and you find the privileges, the bonuses you can get for that, for being a member. Then, of course, my code sheets and data sets are all available on Google Drive. So just check the description box either on Facebook or YouTube, and you can find your way there. Download all the materials and follow step by step because that is the best way to learn coding. Don't forget to like and share this video and every other video on the channel that you interact with so that more people can have access to this great content we have going on here. Till I come your way again, keep doing data right. Bye.